Welcome back. So this is a new lecture now on data modeling. So this is the stack that we are rebuilding, right? This monolithic stack that we want to replace with a modular stack on the running on a cluster. And I would like to do some parentheses to go through lessons that we have learned so far in this lecture, in this course. 10, it's a top 10. So I'm starting with, actually, you know, it's cooler to go 10 to 1, but I went 1 to 10. Okay, let's go 1 to 10. So the first important lesson is learn from the past. Do not make the mistake that some people are doing, that they ignore what has been done before, and they think that everything that is new is in and all the rest is out, right? So relational databases, it's 50 years old, but a lot of these things are still very useful today, and a lot of principles are actually still useful today, even in big data. Always learn from the past. The same goes with XML, JSON, and so on. It's sadly a problem in JSON that we've had is that many people who love to use JSON do not like XML, and so they discard XML a bit too easily. But the thing is, XML and JSON are actually not so different. And a lot of things that are in the XML ecosystem are actually directly relevant to JSON. And so what I have witnessed is things like, for example, XML has XML schema, it has namespaces, it has pointers, it has all kinds of features, query languages. And then at first, people thought, okay, with the simplicity of JSON, we don't need all of that. Except that a few years later, they did realize that after all, they need a schema, after all, they need a query language and so on. And the problem is that many of these developments were reinvented from scratch without learning from what was done on the XML side. And when you do these kind of things, you basically lose time, you lose a few years, you're doing mistakes again that people have already been doing before. And this is, it's a bit sad, right? Because you would be much faster if you could actually reuse what was done before and not redo the mistakes that were done before, right? So really take the time to learn from the past. Consider that the mistakes that our ancestors have been making are useful for us so that we don't do them all over again. So learn from the past. Second, that's about the simplicity. Keep the design simple. This is how you can scale out to thousands of machines or millions of machines, right? So this is the idea in cloud storage, for example, with the key values, the fact that we just have object IDs and bucket IDs, and they give us an object value. That's super simple, flat, and it scales. So this is paramount in computer science to design things that we actually understand. And in fact, that's probably one of the major challenges now that we have with generative AI and ChatGPT is that there is a real risk that we do not understand anymore what we are building. You know, it's hype to talk about like the singularity, the consciousness, and so on, but that's not what it's about. What it's about is we are engineering things, we are building things, and it is important that we understand what we are building and that we build it in a way that our human brains can actually understand what we are doing. The third one is to modularize the architecture. This is what we love to do in computer science, but this is also how a house is built, right? You have some people specializing in building the walls, some others in digging into the earth, some others in putting the electricity, and so on, right? So we modularize the architecture, and this is why we have this stack with the storage, the syntax, the validation, the querying, the indexing, and so on. So this is also one of the ways that we simplify things so that we keep control of what we are building. It's the modularization of the architecture. This is very important to computer scientists, right? If you build systems, you want to build it in a modular fashion. And so when you are somewhere in the stack, there even are names for that, but basically, for example, if you are in here, you are basically using as a physical layer the layer below, and you are providing a service to the level above, right? It's like every time there is a line here, there is a contract, right? For example, here, this might be HDFS, right? That is storing the files in blocks and so on, and that might be HBase, right? But you need to reason on the API right here. If you did not have some communication between two modules, and instead you had a monolithic single system that tried to do both HBase and HDFS at the same time, designing something like that would be incredibly difficult. It is so much easier to first design HDFS and then design HBase, and then think of how they interact. So this is the modularization. And a term that you will sometime encounter is the notion of south and north, right? A south API means that this is the API to the physical layer compared to where you are, and the north API is the API with whoever is using your service, right? Okay. Fourth, the homogeneity in the large. It's the idea that we have collections of millions, billions, trillions, quadrillions of things that at large scale look homogeneous. For example, if you zoom out on cloud storage, what do you have? You just have trillions of objects. Of course, if you zoom in, the objects are different, right? You might have one object that is a Star Wars movie and the other one that is a Star Trek movie. And of course, these are very different, right? But if you zoom out, on the large scale, it's homogeneous, right? You just have a huge collection of trillions of objects or trillions of rows in HBase or trillions of JSON documents and so on. So it's all homogeneous. But if you zoom in, this is where the diversity kicks in. And now this is one of the developments of big data that we didn't have in relational databases, because in a relational database, all of the rows of a table, they look alike. They all have the same columns, they all have the same types. But in order to scale with big data, you need to accept that maybe not every single one of these trillions of objects in S3 have the same size or have the same content or the same file type and so on. Likewise, if you're looking not at objects, but you're looking at database rows in a table, then what that means here with heterogeneity is that maybe some of the rows will have missing columns, some other rows will have extra columns, some of the columns might contain a different type of value, maybe an integer in one of the rows, and then it's a string in a different row with the same column. And so we are building systems in big data that actually support this, that support the heterogeneity for small values, right? So you have a homogeneous, huge sequence of heterogeneous values, so to say. Then the sixth principle is something that I'm doing every week. I'm trying to always tell you things at the logical level and then tell you how it's physically implemented. For example, when I started teaching you HBase, I wasn't talking about HDFS or even files or anything. I just presented to you the model with the row IDs and the column families and the column names and so on. And only after that did I start saying, okay, yes, we actually partition by region and it's assigned to region servers and stored in HDFS, but that's a physical detail, right? And a user of HBase, if somebody else is using HBase for something else, they don't care about HDFS. They only care about HBase's model, right? So this is why we always abstract a logical model from the physical implementation. This is actually also compatible with this, right? It's the idea that every single color here is actually building on top of the color below it. Okay, so basically, the orange color here would be the logical layer compared to the yellow color, that would be a physical layer. But if you look the orange against the purple, then the purple is the logical layer, and compared to the purple, the orange is the physical layer. So this idea of being logical or physical layer is always relative to where you are in that stack, right? HDFS has a logical layer compared to the actual hard drive sitting in the cluster. It's logical, but if you compare it with HBase, then HDFS is then physical. It's the physical layer of HBase. For whom is that clear? Okay. So then we've seen that as well, shard the data. Of course, there's plenty of words, shard, chunk, block, partition, split, what else? There are many, many, many. Shard, block, chunk, partition, split, region, and so on and so on and so on. These are all synonyms. What actually is happening is that we just cut the pie into smaller pieces in such a way that we can distribute it all over the cluster, right? So this is called sharding, partitioning, chunking, and so on. That goes together with replicating, because once you have the chunks or partitions or blocks or splits or regions, then you actually can duplicate them and store them multiple times on one of the layers. So then it means that each one of the blocks or chunks will be stored repeatedly. In the case of HDFS, you store each block 3 times by default, and you can even increase the number of times. So you not only shard, you also replicate. Okay? But it should be clear to you that replication is much easier after you sharded the data. If you don't shard the data, replicating is more complicated. But if you shard the data into blocks that have a size of 128 megabytes, then replicating is easy. You're just copying over files that are 128 megabytes, and that's easy. Okay. Number 9 is the idea of buying a lot of super cheap hardware. This is the secret of a data center, right? We don't try to build some supercomputer with a petabyte of memory and ronabytes of hard drive. No. We just build regular machines that are gigabytes or terabytes of memory, terabytes of hard drives, and then we just have 1,000 of them, right? Or even millions of them, as you saw with Spanner. By the way, the name, I think, of the successor of HDFS, they call it Colossus, is the name, the one that stores across clusters. Okay, so this is the cheap hardware. And finally, the batch processing, this is this 2048 game. It's the idea that we try to avoid reading and writing small amounts of data from the disk because it's super expensive. Instead, whenever we read, whenever we write, we try to read and write an entire batch of data. Right? In the case of HDFS, we try to do it 128 megabytes at a time. In the case of HBase, we do it at the H file level with the LSM trees on multiple layers. But basically, when I told you about batch processing at the beginning of the lecture, these LSM trees are batch processing. Okay? It means that we read and write entire H files at a time. Okay. So this leaves us here. These were 10 ideas of big data, and actually they will follow us through the rest of the semester. And I even come back to them at the end of the semester, these 10 ideas. But now, where we are is we've looked at storage, encoding, syntax, and now we are looking at data models. HBase technically could be seen as a storage as well, because we are going to actually be storing XML and JSON document in HBase. So now I'm going to come to data models today and not next week, but in 2 weeks. Okay, so what is a data model? It's the idea that when you have syntax, and syntax is what we've looked at 2 weeks ago, right? It's a text file that you interpret as XML or JSON or CSV or YAML or whatever you want, but it's only syntax. And if you look at syntax, in your mind, if you look at what's below here with the comma separated value, it's a CSV file. If you read it as a human, you still can figure out that it's actually a table. So if you try to open that file, it will actually probably open Excel or Apple, what's the name of the Apple equivalent, numbers, Apple numbers. So you will see a table. And what's important to understand is that, again, it's physical logical. This is the physical layer where we have actual text. This is the logical layer where we have actually a table. And what do we have in this logical model? We have a model, which means that we have rows, we have columns, and so on and so on, right? This is a data model. You cannot read syntax without having a data model. It makes absolutely no sense. So now we are going to do the data modeling part that corresponds to XML and JSON. Right. So let's start with JSON. And I will give you the intuition of what a data model here is. We saw that when I explained the syntax of JSON, I used the name building block. I gave you 6 building blocks that you find in JSON. There are strings, there are numbers, there are booleans, there are nulls, there are objects, and there are arrays. That's 6 possible ones. 4 of them we call atomic values because they do not nest, right? If you have a string or a number or a boolean or a null, that's it. That's the end of it. But there are those that allow us to nest, which are the objects and the arrays, right? And an object is just a map that maps strings to values, right? And an array is just a list, an ordered list of values. And here we have recursion, because when I say value, I again mean any one of these 6, right? So we can have an array of objects of arrays of objects of objects of arrays of integers, for example. And you can also mix values in the same array. You can have integers, strings, objects, all mixed together. That's then the heterogeneity. All right, but these are 6 building blocks. How can we use, because I presented them as syntactic building blocks, right? But now can we abstract away from this? For example, this is a JSON document. It is well formed. Could actually open it in Oxygen and actually it will confirm that it is well formed. So now my question to you is, if I show you this, who of you, please raise your hands, who of you sees a tree here, a tree structure? On Zoom, does anybody see a tree here, tree structure? Do we have any raised hands? Okay, that's great, because this is what I'm here for. I'm here for explaining that to you. And maybe some of you do, and that's actually awesome. But my goal is that everybody sees a tree structure at the end of this lecture. Right. Okay, so where is the tree? How do we find the tree? Well, what is this on the high level? What kind of value is this? The entire thing. Is it a string? Is it a number? Is it an array? What is it? Yes?
Is it a JSON object?
Yes, it is an object, absolutely. So I'm putting object right there to basically represent what you've just said. Then, what is this object made of? How many keys does it have? You can directly say it. Yes, exactly. Then we have again nestedness. At the top level, however, you are correct, there are 2 keys. Right? So at the level that I'm watching, there is a key foo and a key bar. And if we look at key foo, it's associated with a Boolean, true. And if we look at key bar, it's associated with an array. Right? And then, and you're again correct about this, within the array, what do we have? Well, let's look closer. We have, you see, an object, and we have a null. So I'm putting here the object and the null. And then we look again, what do we have in the object here? We have 1 key, foo bar, associated with a string foo. Who sees the tree now? Right, this is a tree. I just represented my JSON document, my JSON object, as a tree structure. And the depth of the tree has to do with having objects in arrays, in objects in arrays, and so on and so on. The leaves of the tree, these are the yellow squares, these are the atomic values. So the leaves of my tree are going to be strings, numbers, Boolean, nulls, and the objects and arrays are the intermediate nodes, right? Notice how I wrote the keys foo bar. I just wrote them as labels on the edge that connects an object to its values, right? Okay, so this is a visual, it's a visualization. It's the same thing as what we have on the left, but represented as a tree. Now, when we actually process JSON or XML or CSV, we are not going to process the syntax or the text. We are always going to first parse the document into memory and build a tree like that when it's XML and JSON. And when we start querying it and working on it, we will always consider the tree. We even forget about the JSON completely. We forget it, right? We only work with the tree that you see on the right. This is a data model. Okay, so we have 6 kinds of nodes in that tree: objects, arrays, strings, numbers, Booleans, and nulls. Plus we have these key labels when we have an object, the green circles. Okay. This is another example. You can actually look at it offline as an exercise, but we have a physical view of a JSON object. And on top, I have drawn the tree that corresponds to that object. So this is the logical view. And again, put it in perspective with this, right? In the case of CSV, you would have a model that is a table. And in the case of JSON, you would have a model that is based on a tree. Right? And in general, we can do models for tables, for trees, for cubes, for graphs, and even for text in the sense of Google actually has a model of text, even ChatGPT as well, right? But here we are going to focus on trees because they are actually fundamental in big data, these tree models. Okay, now it should be easy since I've done it for JSON, who understand that the same applies to XML. For whom is that here? Okay, very good. And I'm going to take again the time to describe this. We can do the same thing. This is what I meant when I kept saying it doesn't matter if you're using XML or JSON. It's all the same. These are all trees. And once you have a tree, the way you process the tree is the same. It doesn't really matter anymore. Okay. You just need to be aware that there are a bit of difference. There is a bit of difference between JSON and XML. It's minor to understand. But basically, the main difference is that in JSON, the labels, so the keys that you have in an object, in the model, we put them on the, oh, I can go through here. We put them on the edges, right? So these are values, object, 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 and the name of the key is just a label that I stamp on the edge going from the object to the value, right? What about XML? When on XML, these are the names of my elements and attributes. These names are on the nodes, right? Directly. What does it mean? It means that in XML, an element or attribute knows how it's called. In JSON, a value does not know how it's called. That's what it essentially means. Let me explain it here. Let's consider this array 1, 2, 3, right? It's here. Does this array know that it's called foo? No, it doesn't. Look at just the array. It doesn't know there is no foo anywhere. The only reason why we know it's associated with key foo is at the upper level with the object, because we have this foo. But the array doesn't know that it's called foo. In XML, it's different. Imagine that, for example, this element here, B containing the text. Does it know it's called B? Yes, it does. Look, B is right there. So it knows that it's called B. This is the difference. The names of the elements and attributes in XML are on the nodes. In JSON, they are on the edges. That's one of the main differences. Okay. So now we've done it with JSON already. Let's do the same with XML. Well, XML is more complex. So I'm not going to dump everything at you. I'm just going to use what we've seen, a very specific subset of XML, which is in fact all you need to query XML data. So this is an example here of XML document. It is well formed. If you put it in Oxygen, it will confirm. If you click on the blue button, it is well formed. So how do we build the tree? Well, there is actually a standard that tells you how to build the tree. We need a standard for this because it's more complex than JSON. For JSON, it's more intuitive. And the idea is that this standard tells you what kinds of nodes you have. Right? In JSON, we had 6 kinds of it, right? Objects, arrays, strings, numbers, booleans, and nulls. In XML, we have 11, but you don't need to worry about these 11. Many of them we just ignore here. I only care about 4 of them, actually. I care about, and these are known to you, we've already seen them, about the elements, I care about the attributes, and I care about the text. And I added one that is the document. It's so easy, that's just the one you put at the top. It's just an extra node that says this is an XML document. So this is why I added. The others you can just forget. You don't need to worry about them. So just these 4: elements, attributes, characters, text, and the document node. So 4 of them. And then when you go through each one of these 4 kinds of nodes that we're going to look at, they have properties. For example, an element has a name, an element has children, and so on and so on. An attribute has a name, an attribute has a value, and so on and so on, right? Text has characters. So these are properties. So what the standard defines for the data model, that's called the XML information set or XML Infoset, it just defines the kinds of nodes and their properties. So let's do it node by node. First, we have a document It's called an information item. This is just the fancy name for the node. They call them information item. I prefer to call them node because it's easier to visualize in a tree. So let's look at the document node. The document node, I'm going to put it in purple, has children. Well, it always has one child. That is the element that is the root of the document. That's the metadata element. I put it in blue here, right? And then it has a property that's the version, but we don't really care about that. I just put it there. It's version 1.0. Okay. So that is the top of my tree that I'm going to draw is the document node, and it has as a child the element node, metadata. Let's now go to the metadata elements then. So the metadata, sorry, yes, the metadata elements. So that's an element node or element information item. What is its local name? It's metadata. What are its children? Well, you can look, well, it's actually hidden behind the Zoom in the lecture hall, so I need to remove it. I saw there is maybe a question on Zoom. We need to get to this. Okay, what was the comment? Oh, that it's a tree. Okay, yeah, awesome, awesome. That's exactly my goal. All right, so now you see how many children does the element metadata have? Well, you see it has two. It has title and it has publisher. The title element, the publisher element. So I put here title and publisher. What are the attributes? Well, nothing. Metadata has no attributes at all, right? The tag already closes here. So there's no attributes. And what is its parents? Because yes, in XML, you go back to the parents, you know the parents. So doc is the parent. Doc was the document node, right? Okay. So that's the element metadata. Now we know what an element node looks like. Let's look at the other two element nodes. So the first other element node is title. What is its name? Well, it's title. What are its children? Well, what is there inside between the tags? There is only text, right? You see, title opens here and closes there, and in the middle of it, there's only text. So the children, it's just a text node. Then what are the attributes? There's two of them, language and year. So I'm putting them in red, the attributes. So here there's the language attribute and the year attribute, and I'll come back to them after that. What is the parent of the title element node? Well, it's the metadata element node. Title is a child of metadata. Who is with me? Okay, let's do the other one then. That's the element publisher. What is its name? It's publisher. What are its children? Well, there's nothing except text in there, so it's just text. What are its attributes? Nothing. There is no attribute inside the opening tag. What is the parent of the publisher element? Is the metadata element, right? So that's it. We have three element nodes. You see, they have the same properties. Yeah, 1, 2, 3. Okay. Now there's more properties, but I didn't want to bother you with that. So I just focused on the properties that interest us for drawing a tree, because I want to draw a tree here. So that's why I'm putting that here. Okay. Oh, now the attributes. So let's go to an attribute node then. The attribute node year that I put in red. What is its name? Well, it's year. What is its value, or if you want to sound fancy, normalized value? What normalized means is just that if there's extra spaces, they are just removed. Mostly that's what it means. So the normalized value is 2022, so 2022. And what is the parent? Well, actually, the name is owner element, but it's basically the parent. It's the element node title. Okay, you agree with that, right? The year attribute, year, the owner element of it is title, because it's sitting in the title opening tag. And the other one, language, its name, its language, its normalized value is en, and its owner element is the element node title. Okay. And finally, text, we have the systems group texts. That's the characters that it's made of are S, Y, S, T, E, M, S, blah, 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 blah. And the owner element of that text systems group, it's title, right? And finally, ETH Zurich, it's made of ETH space ZURICH, and the owner element is publisher. Okay, so what have I done here? Well, I nicely went through the spec of specifying the properties of every single node that I find in there, every single information item. What can I get out of that? Guess what? A tree. Because essentially, if you consider the children and parents attributes, this just gives us a tree. So then we can draw that, and here you go. That's the tree. So you have some exercises where we give you JSON and XML documents, and we ask you to draw the trees. In order to simplify things, and maybe you can also check with the team, but I think it's the case, we do not have any namespaces there. Namespaces are complicated enough. We are not going to bother you with namespaces for data modeling, right? So we don't have any namespaces in there. Okay, who finds it easy now? If I give you an XML document, you can draw the tree. Who feels able to do that? Okay, and JSON as well. Okay, that's the goal. And now, what I hope we have achieved is that if I give you any JSON object or any XML document, you can draw the tree. That's the goal. That's the learning goal here. And once you have seen that it is a tree, then we can make progress in the lecture to actually manipulate and query these trees and also relates them to tables, because we'll see there is a relationship between the trees and the tables. So what do we do now that we have the trees? That's the first milestone. Well, the next step is called validation. Validation comes after well-formedness. In fact, this is the reason why I told you, if you remember 2 weeks ago, do not use the word validation when you mean well-formedness. Well-formedness means I have a JSON document, I'm trying to open a text document as JSON, and it works. That's well-formed. I'm trying to open some text document as XML, and it works. That's well-formed. If it's not well-formed, I'll get an error. And what's very important is if it's well-formed, then you can draw the tree. If it's not well-formed, you cannot draw any tree. It only works if it's well-formed. Okay. And the next step that now I'm introducing is validation. So validation is another question that you can ask after having established that it's well-formed. If it's not well-formed, you cannot even test for validation. So a well-formed document can be valid or it can be invalid. Now you're gonna tell me against what? Is it valid or invalid? Well, this is the purpose of the schemas. What's important is that in Oxygen, who downloaded Oxygen? Very good, you should. ETH bought it extra for us. They have a site license, and it's a very good way of making sure that you manipulate XML and JSON. So in Oxygen, it depends on the version, but basically it's like the matrix thing with the two colors, right, red or blue. So the blue gives you the well-formedness check. It's going to say, yes, it's well-formed, or no, it's not well-formed. And the red button is for validity. It's going to tell you, yes, it's valid, or no, it's not valid. Moreover, validation is a yes-no answer, but it comes together with something called an annotation. If you manage to validate a document, you can also annotate it. I'm going to give you a specific example here of what annotation would mean. If I parse this as XML, systems group, ETH Zurich, 2022 EN, these are just characters. This is just text. However, I might want to validate this document against a schema that says that the year attribute expects an integer. So, will it succeed? Yes, of course it will succeed, because 2022, we can interpret that as an integer. So the validation will say, yes, yes, absolutely. Not only is it well-formed because we managed to do the tree, but on top of that, it's even valid against a schema that requires the year to be an integer. Annotation means that at that position here, I'm gonna go back here, we actually replace this with an actual integer in memory, 32-bit integer. This is annotation. I remove these two, this 0, this 2, and this 2, and I replace it with the integer 2022. This is annotating, okay? Who understands? Okay. But of course, we'll spend the entire lecture on that. So this is only the appetizer here, and we'll go into the details of that. Okay. All right. Now, let's dive a bit more into this idea of validation against what? because unlike well-formedness, validation is not absolute. Well-formedness is absolute. I give you a text document, yes or no, it's well-formed, period. Validation depends on a schema. You need to give a schema with your expectations. You expect this to be an integer, you expect this and that structure, and then you ask the question, is this well-formed document valid against my schema? So what is going to happen if now you validate not one document, but a million documents? You have a huge data set with plenty of JSON documents, a million JSON documents. Then you come with a schema that says, I want this key to be an integer, I want this key to be an array, and so on and so on. What's going to happen if you successfully validate your data sets, then it means it's actually homogeneous. So if you successfully validate, you are here. You actually have a homogeneous collection. What it means is that all the objects look alike. They have the same keys. The keys are associated with the same kind of values and so on. As opposed to having no schema, and that's also totally fine to have no schema. Maybe you want to stop at well-formedness and just have a well-formed collection. But then you're going to have a lot of heterogeneity in there. Because if you do not validate against any schema, then you could throw any objects you want in there. There will be an object with a key foo that is an integer, another one with a key bar that is an array, and so on. And you can have a heterogeneous collection with millions of documents that have nothing to do with each other. But this is the flexibility of big data. You are not obligated to validate. This should be contrasted with relational databases. Because if you look at PostgreSQL and relational tables, in relational tables, you start with the schema. If you don't specify the schema of your table, you cannot even put any data in there. It's the first step to come up with the schema in a relational table, right? So it means you say, okay, these are my columns, and these are the types of my columns, and then you put the data in there. So in a relational database, the data is always valid. It's always valid because if it's not valid, you would not even have been able to put it in there, right? So by design, the system makes sure that the data is always valid. In the case of big data and XML and JSON, we are more flexible. We do not require the data to be valid. We don't even ask for a schema. You just pour your data in there as it is, right? Whatever XML and JSON you have, and you delay the process of validating. You do it later, right? And now is this later, where we can actually worry about whether or not the data is valid or not. One of the uses of validation is machine learning. If you want to feed the data in a machine learning system, these good old machine learning systems like classification, regression, and so on, then you need to clean up your data and validate it. Okay. Now, concrete example. This here is a mess. This would be tough to validate. You see the B is an array, but it has the string, it has a Boolean, it has a null, it's an object, it's a huge mess. E is an array, but look what else there is in there. There are integers, but there's also an nested array, so it's a huge mess. This here is the intuition that I would like you to have about what happens if we do not have any validation in there. We do not validate anything, and we just have some heterogeneous data. This here is the sort of document you can validate. Do you see the structure here? Right? We have C that is an array, but look at what there is in this array. There is a key foo. It's always a string, bar1, bar2, bar3, right? So it's a string. And bar is another key. It's optional because the third doesn't have it. The third object doesn't have a bar key, but this is fine. That's acceptable. And then bar is what? It's an array of integers, always, both on the first and on the second case. This here, we can actually validate with a schema. The schema will basically say A is an integer, B is a Boolean, C is an array of objects that has a key foo that is a string and a key bar that is an array of integers. That's my schema. Okay, who is with me? Yeah. All right. So this is what we are actually going to achieve. And actually, we'll give you technologies, 3 of them. There's JSON schema, JSOund, and XML schema. Spring is coming with the allergies. So we are going to have, in 2 weeks, the actual way to design your schemas. I'm going to show you how this is done. And before we actually do that, I'm going to be probably also in 2 weeks telling you about the type system. Why is it so important? Because I told you that when you look at well-formedness, you don't care about types. In XML, you only have text. In JSON, you only have numbers and strings and booleans and nulls. That's not a lot. What about dates, for example? What about times? What about binary objects like images? So you need a type system. So when you have a schema framework that allows you to do this kind of things, to validate your data, you need types. For example, here you need to be able to say that 1 is an integer and 2 is a boolean and so on. I have good news, and maybe that's going to be my last slide for today. I have very, very good news for you. There are tons of technologies out there that allow you to validate data or store valid data, tons of them. XML schema, JSON schema, JSON, there is also Parquet, Avro, protocol buffers, even SQL, and so on and so on. Even Java programming languages have a type system. What is the piece of good news? The piece of good news is that the ideas, the general ideas of the type systems, they're always the same. What that means is that if you learn in a generic way, the way that type systems work, then you'll be able to very easily understand any of them. So I'm going to start next in 2 weeks with an overview of the type system in a generic way that is totally agnostic of the technology we look at. And then we'll be using the type system specifically for JSON schema, JSON, and XML schema. But my expectation is that then, after this course, you can look at any other kind of technology, protocol buffer, and so on, and it should be a walk in the park for you to understand them. Because you'll just be able to see that in the end, maybe the names are not the same, right? But it's always the same ideas and the same patterns, right? And so in 2 weeks, I'm going to come back on what these bullet points actually mean, and we are going to go into all of the details. And again, to be able to validate this kind of beautiful documents. All right, so now I'm approaching the end. So do I have? Yes, that's the one. Hopefully it still works. Yes, now you can proceed. So this is it for today. Thank you very much for attending. Now we have an Easter break, so there is no lecture next Tuesday. There is also no exercise session next Tuesday, next week. And so I'll see you in 2 weeks at 8 a.m. for the lecture, and then we'll dive into the type system. So, oh, did I start it? It's not appearing on my screen somehow. Probably the computer is already in the Easter break. Oh no, I need to show here, that's why. Yeah, all right. Okay, so still a majority in the 80% bucket. So make sure you read the chapters of the textbook. This is what it's for, right? You can read in more details everything I'm explaining to you. Enjoy the exercise sessions that will be on HBase, I think. And I'll see you in 2 weeks. Thank you very much.